We're going to look at this problem now. It says a tension test was performed on a magnesium specimen that is 2 inches in length and 0.5 inches diameter. And the results are shown below in this picture. And we have to estimate Young's modulus and estimate the yield stress of the material using the 0.2% offset method. So that's part A and B of the problem. Then there's going to be a part C here in a few minutes. So now that for part A, it's pretty straightforward because you can just use the formula that the Young's modulus E is equal to the stress divided by the strain. We have to look at just in the proportional area. So like, for example, just along the straight line, we don't want to consider anywhere where it gets near this curved part. We just want in the proportional area here where there's a straight line to see if we can find a point where we can read the stress and read the strain. You could really use any point along the straight part of this line, any point that you could read. You could maybe try this one here. This would be maybe 6.5 KSI, and then 0.001 for your strain. Or perhaps you could use, this is starting to get near the curve part, but it looks like it's still straight up here. You could possibly use this one here, which is maybe what, 12.5 KSI and 0.002 for the strain. That might be our best choice. We'll pick this point right here. Again, we can't pick anything over here where it's starting to curve. So we went just in this first proportional region here. And so again, if we pick this point here, again, it looks like about 12.5 KSI, which means about 12.5 PSI, or excuse me, 12,500 PSI. And then divide by the associated strain. That's this point right here, 0.002. Remember, strain is like inches per inch or feet per feet. And so that's going to give us $6,250,000 pounds per inch squared is going to be our Young's modulus. And as I said before, you could have picked another point here. Like I said, you could pick this point or any point, probably again, whichever point you could read the best. You know, again, this is just going to be a rough estimate. So the other thing we have to do, we have to estimate the yield stress of the material using the 0.2% offset method. So again, the yield is going to occur somewhere along here where you start to see this curved region, but it's always very, very difficult to estimate where the yield actually begins. So usually what they do, they'll usually use like a 0.2% offset method or 0.3% offset method. And what that means is, of course, 0.2%, if it in decimal form, would be 0.002. And so what you want to do is start here at the 0.002. Start down here at 002. and make a line parallel to this first proportional region here. So we would maybe pick, again, starting at this point here, and try to see if you can make a line that's parallel to this proportional line. And again, sometimes it's difficult to do this real accurately, but it looks like that's probably pretty close. This line here is going to be pretty much perpendicular to that line there. So let's draw this line up here. So again, you can see we started at the 0.002 because it's a 0.2% offset, and we made a line parallel to this proportional region. And so this, you can see this intersects right here, and that's going to give us the yield stress right there. And so read this over here, looks like it's reading about right there, maybe 26 KSI. So the yield stress is about 26 KSI, or 26,000 pounds per inch squared. So the next thing that we're asked to do is estimate the permanent elongation. Let me show this here. The part C says we're supposed to estimate the permanent elongation of the specimen if it's stressed to 30,000 KSI. In other words, what will be the new permanent length of the 2-inch specimen after it is stressed to 30,000 KSI and the load is released? So what's happening here is when we get up to that range, like 30,000 KSI, we're past the yield point, and we're well past the proportional limit. So anytime you get up here, when you release the load, it's not going to go back to its original length. It's not going to go back to zero deformation, but it's going to go to some permanent deformation. So let's start here again, starting at our 30,000, which was right up here. And so what we want to do, start at the 30,000 and then make a line. Once again, we're trying to find a line parallel to this proportional area here. So we're going to come up here. And again, it's not always real easy to do. Again, these are just estimates, so there's going to be some variation in the answers. It looks like that's going to give us a line parallel to this proportional region here. So those two are going to be parallel there. And so again, we started the 30,000 and went back. It looks like, and then wherever we intersect here, that's going to be the permanent strain. So it looks like we intersected here around 0.003 strain. And that means that's going to be the permanent strain in the bar now. And so to find the actual deformation, So the deformation or elongation, the permanent, so delta in the permanent is going to be epsilon times our length L, which is going to be 0.0003 times our 2-inch length, which when you put that in your calculator, you get 0.0062 inches. So that's going to be the permanent deformation. So that means the new length, the new permanent length, is going to be your original length, your original 2 inches, plus your 0.0062, which is 2.0062 inches. That. Now, this particular graph did not show, the material breaking, so it doesn't show the ultimate tensile strength. So if they had given us a curve, let's say, in fact, here's a diagram from Hibbler. Like if they had given you the curve all the way up, and so like they gave us sort of just this part down here, they gave us for the example where they gave us just this part down here. But if they'd given us the whole curve, the peak would have been the ultimate stress. That would have been the peak if they had shown the peak on our graph. And this is just, but again, this particular problem didn't show that, but that's just for future reference.